Hello and welcome back to Calculus 1 section 4.8 on Newton's method. So what do we do here? Well, we are approximating or calculating the zero of a function. So we use it to find zeros. Now, what is a zero? Zero is where the function cuts through x-axis. This is literally where f of x is equal to 0. That's why it's called zeros, right? Or it's also known as root, and it's also known as x-intercept. Now, that is very easy to come up with if you have your function to be, let's say, y equals 3x plus 6. It's like, yeah, 3x plus 6 equal to 0, x equals -2. Easy, right? So that's your zero or a root or whatever you want to call it. Also easy when you have a quadratic, like x squared minus 4x equals 0, right? Oh, factor out x minus 4, set each one of these to 0, x equals 0, x equals 4, easy peasy, right? So zeros. So it's easy when it's nicely lined up. But when you get some of these equations, right, and it's just like, holy nightmare, we can't solve it nicely, especially if it's a polynomial. Polynomials are the nastiest functions out there for zeros, right? Because even with a quadratic, if you can't factor it, right, you have to use that quadratic formula, which is already all of the operations in a book other than ln are in it, right? But when you try the cubic one or the quadric one, just look them up online, right? They can take like 20 minutes to an hour to use those formulas to just find the root. And then there is a proof that you can't have a formula or a procedure for a polynomial of power 5 and above. So yeah, wow, right? So what we do here is we come up with this method. Well, Newton came up with a method that you can use to find the roots. And obviously this was beyond brilliant at his time, because remember, no computers, no calculators, no any of the tech to do the calculations for us. And right, all of the functions, almost all of the functions around you are just polynomials. And you can't get the roots for anything that it's of a power 4, 5, 6, 7, because just you can't. So what did he do? He said, if I have, a function cutting through x-axis somewhere, and I don't know what this is, if I pick some value a somewhere, and then I go and I find a tangent line at that point, that tangent line is going to give me a new value. Then I'm going to use that value to come up with a new tangent line, and that's going to give me another value. That value is going to give me a new tangent line. Ooh. If I just keep doing this and doing this and doing this, eventually, right, maybe I do it 4 or 5 times, the value that the tangent line cuts through on x-axis is actually the value that I'm looking for, C, right? We started all the way here, but then the tangent lines brought that A into A1, A2, A3, A4. So if you go far enough, right, that A gets very close to C. It doesn't become C, but it's close enough to the like 5 decimals, 10 decimals, depends on how far you go with your calculations. Now, without going into iterations here and proof of how all of this is done, but you can follow the picture, right? All of this gets to be put into this one iterated formula where you can compute your xn plus 1 as xn and then correct it, right, with the tangent line, with each f of xn divided by f prime of xn. And you need initial guess. X0 equals some value. Now you have to provide that value. And clearly you can't have your f prime be 0 or anything like that. This is your Newton's method right here. And all we need to do now is to just compute an example. So, practice exercises. How about tangent x minus 2x, because we can? Like, what's the root of that? So f of x is equal to tangent x minus 2x, and our x0 initial guess is going to start at 1.2. Now, when I used to, go to school many moons ago, but it was still in the era of TI-83, 84 calculators, we got to program this on a calculator and use the software on the calculator. Now, you guys have much better options of Java and Python and so on. So even if you are not computer science major, you should be able to program such a basic thing in one loop with one formula, right? And ask for input of a number. So how does this work? Well, there I say clearly, I need to find the derivative because derivative is in the formula. Now we know that the derivative of this is 1 over 1 plus x squared minus 2. All right. We also know that the root that we are looking for is an x value that is eventually going to pop up when we start calculating from x0. So what is my x1? x1 is x0. You see how these are all, this is like one more than all others. So when this is 1, all others are 0. When this is 2, all others are 1. So that's how you compute this. Because now I'm going to use my x0s to compute everything, which is 1.2 minus tangent 1.2 minus 2 times 1.2 divided by 1 over 1 plus 1.2 squared minus 2. So all I did is I took, this is x0, right? This over here is the original function computed at 1.2. And this on the bottom here is the other function, which is the derivative function computed at 1.2. And all I need to do is this arithmetic, right? I don't do anything else. Now, guys, if you are using calculator to calculate, well, you should be using calculator to calculate tangent of 1.2, make sure your calculator is in radians. Okay? Right? Radians. Because 1.2 radians and 1.2 degrees is not the same thing. Is 1.2 radians in the first quadrant? Yes, it is, but it's closer to 90. And 1.2 degrees is almost like 0 degrees, which is closer to x-axis. So be very careful about that. So how much is your x1? Well, it's 1.2 minus, now you change your calculator to radians. Your calculator should be in radians if you're not doing engineering anyway, right? Because all math is done in radians. So you have your tangent of 1.2, and that gives you 2.572, let's say, and then minus 2.4 when you multiply that, divided by, now on the bottom, I have 1 divided by, open parenthesis, 1 plus 1.2 squared. That's going to give me 0.4098, and I'm supposed to subtract 2. It's just a lot of decimals and a lot of calculations that the computer should be doing. So this is 0.172 divided by negative 1.59002. I can just call this that. So this works out to be 1.2 plus, when I get these two minus signs, and now 0.172 divided by 1.59 is 0.108, which gives me the value of 1.308. There's my x1. Rinse and repeat. x2 is x1 minus f of x1, f prime of x1. Plug everything in. 1.308 minus, the original function is tangent of 1.308 minus 2 times 1.308 divided by the derivative, 1 over 1 plus 1.308 squared minus 2. Can you calculate that? You get your x2. Then you go x3, x4, x5, x6, x7. Eventually, you already see that between your starting point of 1.2 and your new point of x 1.3, this 1 point is common. So that's fixed. Your answer must have 1 point. Now, if your answer x.2 ends up with having a 3 next, then that's pinned as well. And the more you go, the more of the decimals you uncover for the answer. Now, you might go into 1.4, in which case 1.3 is not fixed then you have to do another one, and so on. So now we calculate this mess. So x2 is going to be all of this. Now I'm going to do that in like 2 shots on a calculator. I'm going to put the entire numerator, which is a tangent of 1.308, close the parenthesis, minus 2.616. So the top is 1.101, and the bottom is 1 divided by, open parenthesis, 1 plus 1.308 squared. And when I do that, I subtract 2. There we go. So that's going to be negative 1.6311. Now this is going to be a plus again. So I have 1.308 plus 1.101 divided by 1.6311, and that's going to give me, oh, I don't like this, 1.983. I typed something wrong somewhere. Now I gotta do all of this again. This is why we have programming. Tangent of 1.308 minus 2.616, because 3 times, yeah, and 2 times 16, good. So the top number is good, 1.101. Okay, probably the bottom number is what I got it wrong. So when I do this division, and then I have 1 plus 1.308 squared. What's the problem now? Oh, okay. And then I subtract 2. Yep. That's good. So now when I divide 1.101 by 1.6311, yeah, I'm getting the same value. I guess that's x2. Everything is fine. I did the calculation. All right, x3 is going to be x2 minus f of x2. You get the idea. And then this continues for as long as this fluctuation stops between these answers. So this is why you're supposed to program this rather than go and compute this 5,000 times. So I'm going to compute one more, and then I'm going to give up. Tangent of 1.98. Oh, by the way, when you're taking class at Rutgers at NJIT, you have to do all of this by hand. They don't give you even the basic calculator. Yeah. So there you have it. And then we have 1 over 1 plus 1.983 squared minus 2. So what's our x3? It is 1.983 minus, the top is tangent, 1.983 minus times 1.983. The top works out to be negative 6.253 divided by, now the bottom, 1 divided by, open parenthesis, 1 plus 1.983 squared, and then all of that minus 2 gives me negative 1 plus 79725, blah blah blah. So these negatives cancel, so I have 1.983 plus 6.253 divided by 1.797. It's getting worse. 5.46. I might have a mistake somewhere, because these numbers are now, instead of getting better, they're getting worse.
Was that subtracted?
Yeah, I did. Did I subtract?
Oh, you added the fraction instead of subtracting it.
Oh, I'm adding it, yeah, because you have two negatives here that cancel. Oh, yes, I'm supposed to subtract. You are right. Second entry. Okay, so I'm getting now negative 1.49. 7. Okay, at least it's close to 1.2 where we started. Now I'm kind of interested to see where is my what the answer is, and to see if I'm actually getting something really bad here, or let's see. What is the problem? It's tangent of x minus 2x. I am supposed to get this value of 1. So we are shooting for x equals 1.165 plus minus, so on both sides. 165561. Okay, so that's still around there. It should settle eventually if I didn't make any of the mistakes. But the way you do this if you program this, you just say to the computer, which is what the computer actually does, just give me, the first 10,000 loops, right? You make the computer do it, and the computer will still take 1 second to do 10,000 loops. I had a student program something for linear algebra, for differential equations, and made the computer do 1 billion calculations. It takes few seconds still, right? Because, by the way, that's what your gigahertz means. How many operations can it do per second? And if you're talking in a gigahertz, that's billions. So there you go. So it's the formula. And all you need to do is to plug into that formula. You plug function into function, derivative into derivative. And then you plug in your x1 everywhere, or x2 everywhere, or x3. And then when you do that 10, 15 times, whatever, the value usually settles around the... so I don't know how many iterations we would have to do here, these calculations. I'd maybe go to x15, I don't know. Add another 2 hours of arithmetic to have it settle at one of these values. Again, not a major talking point because we have computers to solve these things for us today, so we don't have to worry about Newton's method and doing it by hand. Now, obviously, computer science has to worry about it because they're the one who program the software that we all use. So yeah, as much as everyone else in the class can say, yeah, whatever, like the computer science people are like, ooh, this is something I can program so everyone else can use it, and that's where I make money. So yeah, different lives, right, and expectations. That's it for Newton's method. It's like one formula which you keep using until your number stops, until your numbers that you get, those x values, until they stop changing rapidly. They settle. Let's say you have 2 decimals that haven't changed in few iterations. It's like, okay, yep, that's it. We got it. Any questions, concerns, anything about Newton's method? All right, then. I'll see you during office hours if you have any questions.